Hello, today we're going to talk about masonry shear wall design for both wind and low seismic loads. My name is Sam Rubenzer. I'm a founder and managing director here at Force. I'm a licensed structural engineer in the state of Illinois and a professional engineer in a lot of Midwestern states. I have an engineering degree from the University of Minnesota and an MBA from Marquette University. Here at Force, we've been consultants to the masonry industry since 2010. We do a lot of presentations such as this one, and we do a lot of papers for design, including a lot of stuff on masonry design. So today what we're going to do, the learning objectives would be exploring different types of shear walls, masonry shear walls that are in practice. We're going to build a little bit of knowledge about shear wall design procedures, best detailing practices, talk a little bit about how to make masonry shear walls more efficient, more effective, and then look at a little bit of just some design tips for modeling shear walls in software programs. So the overall agenda would be to talk about shear walls. We're going to look at load-bearing, non-load-bearing walls, kind of talk about some of the differences there. Talk a little bit about hybrid walls, how they can be used in practice. Shaft walls, what are some of the benefits of masonry shaft walls. We'll then look at some masonry shear wall details and some suggestions for detailing masonry walls to, again, get more capacity out of your designs. We'll go through a few examples, and then we'll wrap up. So first and foremost, the things that we want to make sure that we have is we have to make sure that we have the right strength of materials. Always a really important thing to have a design checklist, such as this one that we have created here at Force, making sure that you have the right materials, utilizing all the strength that you can for masonry shear walls. For doing that, you certainly can use the code. The code is going to give us some really simple methods for determining the overall strength of masonry. Code has this, which would be called Table 2 in the TMS code, which is going to give us some strengths of masonry based on different types of mortar, different types of block strengths. For me, I like to reorganize this table a little bit. I like to start from left to right, thinking about the blocks that are going to be supplied to the site, then placing it within a certain type of mortar. Type S mortar is going to be what I would prefer to use for masonry. And then that's going to give us our overall assembly strength. So it's the same table, just a little bit reorganized from what's in the TMS code. Just a little bit more basic information about mortar. Obviously, mortar's a little bit different than block. It's the glue that is used to hold units together. We really want to make sure that we specify types of mortar. There's certain types of mortar that you need to use if you're going to be in moderate to high seismic region, so we certainly need to be aware of that. But mortar is definitely going to be something that we need to pay attention to in determining the overall strength of assembly. So again, we know what the blocks are. We place them within mortar types, and that's how some of these tables are going to come together. Grout's going to be a little bit different. Grout's going to be kind of a dependent variable in the sense that grout is going to be a strength that we have that's at least 2,000 psi. But then it might need to be stronger if we have stronger blocks, stronger mortar. We have a design strength F'(m) that's a little bit higher. It could be that the grout needs to be higher than 2,000 if the F'(m) from the block and the mortar would be stronger. Other really important aspects of grout, it needs to be fluid. It needs to flow into these confined spaces. It certainly has got some very important strength properties. Grout can be made up of different types of aggregates, different types of admixtures that can make it fine, coarse, or self-consolidated grout. It's not the same as mortar, has quite a bit different properties. It is a concrete material, but again, a little bit different properties. But like I said, looking at all the different elements here, we have the code that we can utilize in Table 2 with the units and the mortar type. And then once we understand all of that, then we can find out what the actual strength of grout is. So just a little bit on some of the basics. Again, why is F'(m) so important? Why is strength of materials so important? For making the walls as efficient as possible, we definitely want to make sure that we understand what the actual strength of masonry is. So that's always going to be important for us in design to make sure that we can understand what our full capacity is so we understand how to make our designs more efficient. That doesn't mean that we should arbitrarily choose a higher strength F'(m). What we should do is we should find out what the materials are local to the site, at least understand what the available strength is, start that with a baseline, and then work up from there. Certainly with shear walls, since we're talking about shear walls today, it does actually matter quite a bit when we have masonry shear walls that are combined with steel or wood or other elements, the actual strength of the masonry walls it does make a big difference, because the way that the program is going to distribute loads, especially if we have a rigid diaphragm or semi-rigid diaphragm, is going to be based on the stiffness of the materials. So if we have a very stiff concrete masonry, but we arbitrarily choose a lower strength masonry material, then that masonry wall won't get enough actual load assigned to it. So that can be a big problem. And so we'll just take a really quick look at an example here. If I just use an F'(M), choose a value that's arbitrarily low, again, 1500 is what we used to use. So we're just going to use that for an example. If I increase it to 2250, which would be much more likely and appropriate for today, you can see what the actual load that gets associated with these walls. See how that load gets associated with the walls is going to be a little bit higher when we have the higher strength of masonry. Elastic modulus is higher, the stiffness of the wall is higher, so we have about a 6% shift in force, and it's about 30 kips. It's not nothing. It's definitely something that we should understand. Now, if I even went further, maybe the F'(M) is actually 3,000 or maybe 4,000. If we have really strong masonry, we arbitrarily choose low numbers, you can see that the distribution of force would be proportionate to some of those change in values. So it's really important to understand what the strength of materials are. What I always try to recommend people is, if you're using a finite element analysis for masonry design, be as accurate as possible, and get a design. And if you wanted to be conservative with your designs, choose to do that in the design step, not in the modeling and analysis step. So again, F'(M) matters, how we model these elements matter. And so it's just a really important tip to recognize. Different shear wall types. Again, we'll go through some of the different definitions for some of these elements, and then we'll look at some of the different shear wall types that we have. Wall, it's a pretty simple definition that we have in the TMS code. It's just a member that defines spaces. Load-bearing walls are going to be something that has more than 200 pounds per foot, in addition to the self-weight. Shear walls are just going to be elements that are going to resist in-plane shear forces. If you look at those, especially for seismic, then we have to get into different categories for seismic. So they have different detailing provisions. If you have an ordinary plain unreinforced wall, that's going to have different provisions than if you have ordinary reinforced shear walls or intermediate reinforced shear walls or specially reinforced shear walls. But what does all that mean? All of that really kind of comes down to when we have a shear wall element, we have to look at the axial forces that we have on the wall. When we determine what the axial forces are, maybe we look at the axial stresses due to the self-weight, due to dead load, so on and so forth. Then we have some moment, some in-plane moment that we have to account for, and what the forces are going to be there, and then the shear forces that are going to be in the element as well. Within the code, again, we're not going to get too deep into this. We have the different capacity equations that come directly from the code for the overall axial and flexural strength. So the different equations that you can see here directly from the TMS code, giving us strengths for different H over R or slenderness ratios. You have different equations that you're going to choose for something that's going to be very thin and tall, would be equation 9-14, or something a little bit more stout would be equation 9-13. We also have shear provisions that we need to look at for our shear walls. Obviously, we have shear capacity that's going to be comprised of both the masonry strength and the steel reinforcement strength. And so when we have our masonry shear walls, we can look at, again, moment to shear ratio, moment to shear divided times the length of the wall. If it's less than 0.25, then we have a little bit higher capacity. If we have a higher moment to shear times length of wall ratio, then our capacity actually drops down. We could have some values in between there, and so we can kind of linear interpolate. But again, those are going to be the capacities for the for our masonry shear walls. Again, you look at the equations on the right, you can see what the actual masonry capacity would be. Again, the equations for the masonry capacity, and then the lower right, you can actually see the reinforcement capacity that you can have in a shear wall. So again, for a little bit of a summary side, moment capacities, you can look at the axial over the area. If it's less than or equal to 0.2 times F'(M), Then you can see what the overall capacity would be. If it's a taller wall, then we have a less lower capacity for 0.05 times F per mm, but the factored moment is going to be here. Nominal capacity is just going to be the area of steel times the strength of the steel plus an axial component times the moment arm that you would have for your design. And so again, looking at the equations and diagram, you can see with the sum of the forces need to equal to 0 for the moment capacity of tension and compression that have to equal some net force. And again, all of this coming from the Masonry Society code book, the TMS code book. We can actually determine what the overall capacity equation, the axial flexural capacity equation would look like. Some things that are really important to recognize from this curve is obviously you can have different moment capacities dependent on the actual axial forces that you have on the design. You can see a point of pure flexure where it's 0 axial force. So again, for a vertical wall, we don't ever have pure flexure. We always have some axial force just due to self-weight that we have to account for. But if we're looking at, say, a horizontal span, we could have a pure flexure type of situation that we need to look at in our design. But it's also good to notice that as you add axial force, the actual moment capacity goes up to a certain point, to what we call a balance point. So we add more moment capacity if we can add more load. So that's why load-bearing shear walls have more capacity than non-load-bearing walls up to a certain point. And then certainly if you have a significant amount of load on the wall, you can certainly diminish the moment capacity and it comes back down. For that, again, the TMS code, it gives us other provisions in here for reinforcement, where reinforcement should be located, the maximum spacing of reinforcement, ratio of vertical reinforcement to horizontal reinforcement, and then the shear capacities that are defined by code. So all of that is going to be within TMS 402 code. Some of the different detailing provisions for the different types of seismic masonry walls. So an ordinary plain wall would have no reinforcement. If we get into detail plain or ordinary reinforced masonry shear walls, we can see some very simple provisions for the amount of vertical reinforcement. So 0.2 inches squared at the corners, or within 16 inches of each side of the opening, within 8 inches of each side of the movement joint, within 8 inches of wall ends, and a maximum spacing of 10 feet on center, 120 inches on center. So very lightly reinforced walls would be considered the ordinary reinforced masonry shear walls. We also have some provisions in here for horizontal reinforcement. We can have 9-gauge wire at 16 inches on center. That works. Or we can have a number 4 bar at 10 feet on center horizontally, which would be enough horizontal reinforcement. And that's generally what we're going to have in there for the shrinkage and temperature reinforcement as well. We also want to make sure that we have horizontal reinforcement above and below openings at 24 inches or 40 bar diameters past the ends of the openings. So we want to make sure that, again, we have good reinforcement so that we have, again, a little bit of a ductile response. Again, it's an ordinary reinforced wall. If I go to intermediate reinforced walls, so that does make a little bit of a difference, that's where we're going to start to limit the vertical reinforcement spacing at 48 inches on center. If we get into some of the higher seismic design categories, then we have to go to especially reinforced masonry shear walls. So then you can start to see more provisions for maximum spacing to be a third of the length of the wall, a third of the height of the wall, 48 inches on center for running bond, 24 inches on center for stack bond. We have reinforcement ratios that we need to make sure that we take into consideration as well. So all different detailing provisions for special reinforced masonry shear walls. I said it's tied to seismic design category. So here you can see a seismic design category, what some of the different steps would be. So a seismic design category A, so a lot of the country can actually be in seismic design category A or B, whereas shear wall must be at least a detailed plane shear wall. We get into seismic design category C, a shear wall can be at least an ordinary reinforced shear wall. Maybe needs to be intermediate that can give you a little bit better response characteristics. And it's not until you get to seismic design category D where you need to have a specially reinforced wall with all the additional provisions for design. You can see within the specially reinforced walls, within seismic design category D, we also have different types of provisions for the mortar that we need to utilize for our designs as well. Some of the different characteristics of seismic design or response modification factors, you're going to see that those are different. So obviously, as we have more reinforcement, we have more of a ductile response so that we can actually use a lower design load for seismic design. So that would be the higher R value, right? So R value of 2 for the ordinary reinforced walls is going to give us a higher shear load that we have to design for. That works for AB seismic design categories A, B, and C. Intermediate reinforced walls give us a higher response modification factor, 3.5, better ductile response. So again, if you wanted to lower your seismic shear forces in seismic design categories A, B, and C, you can certainly choose intermediate reinforced wall, which again really just sets the reinforcement spacing at 48 inches on center. Pretty small consideration there. Specially reinforced, we can go to the response modification factor of 5, and that's really what we have to do when we get to the higher seismic design categories as well. All right, here, so we'll go talk a little bit more about some of the load-bearing, non-load-bearing steps. Load-bearing walls, again, they're going to have not just the bend, so you have bending force that comes to the shear. You'll have some tensile stresses. You'll have some compression forces from the pure bending. But we all have self-weight for all of these walls, and that's going to always give us some compression. Again, where the walls are going to land, can it actually be unreinforced? Well, if you have enough self-weight plus additional load, you maybe don't even have any tensile forces in your design, because concrete masonry is a very good material in compression, not so good in tension. We know that we have small tensile properties, but if we can have self-weight plus some axial force on the wall that keeps the wall from having any tensile stresses, that certainly allows the unreinforced masonry member to remain uncracked, and that certainly can work pretty well. Reinforced masonry walls, obviously, if we have a higher demand on the shear and moment forces and higher stresses, maybe more than any of the additional weight plus self-weight that we can add, then that's where we're going to start to look at adding some reinforcement, because reinforcement is going to be a lot better in tension. Again, we have some small tensile properties that you have available from masonry, but again, if it gets anything more than some nominal small tensile forces, adding reinforcement is certainly going to increase the overall capacity, moment capacity, and shear capacity for that matter of the masonry shear walls. So certainly something that we would move to pretty quickly. And again, for those non-load bearing elements, you have a lot more tensile forces. So again, we just have the self-weight and the shear forces. So what we're going to have is we're going to just have more tensile forces that would be accumulating in the masonry shear wall. So maybe more of a demand for reinforcement than if you have some load on the wall. So non-load bearing walls certainly can be shear walls, can be pretty effective as shear walls, but there's likely going to be more reinforcement that's needed in those type of designs. So with that, let's jump over to hybrid walls. Hybrid walls are going to be a special type of shear wall, because a hybrid wall is going to be a masonry wall that's going to be built within a frame. It's going to be built within maybe a steel frame or a concrete frame. It's going to combine with the overall elements, and it's going to give us our design shear forces just due to the nature of masonry being a rigid element. Why do they choose a hybrid design? A lot of times it could be maybe a steel construction project where the steel contractor wants to go all of the steel members all at once, and then he wants to come back in and infill with masonry. That's one possibility. But it's really kind of meant to eliminate situations like this where, again, you can have a steel building and a steel brace that cuts through the masonry walls. But I would say about this is it's going to be a pretty inefficient use of materials. The masonry elements are going to be more expensive, having to cut and fit around a steel brace. The masonry elements are also going to be more rigid, so it's quite likely that they're going to take some of the stress that was meant for the steel brace because of the rigidity of the masonry elements and the overall gross area of those masonry elements. So oftentimes we see that this is going to be a more costly and less effective type of situation. So hybrid designs are really meant to allow the steel to be there for construction purposes, but then allow the masonry elements to be maybe non-load bearing, maybe load bearing, but allow those elements to be the shear wall elements for that design. So here's a couple diagrams to show if there's a gap on the sides and gap at the top. We would refer to that as a type 1 hybrid design, where again we have some in-plane shear that we can associate with the wall, but it's going to be a non-load bearing masonry shear wall. So again, maybe a little bit more reinforcement. If you get into a type 2 hybrid design, that's where the steel is going to be actually sitting on the masonry wall, because maybe we put the steel in there first, but we build the masonry tight to the underside of the steel element. So that allows that to be a load-bearing masonry wall, masonry shear wall, which that can again be more effective in the overall design. There's actually a couple delineations. Type 2A can be the tension tie down, so you have some tension and compression capacity that you can develop for this design, based on maybe it's sitting on a foundation. It's pretty easy to have dowels into the foundation. We could have the shear wall be effective in that respect. Or you could go to a type 2B where you don't have any of those tensile forces. Maybe this is going to be typically used at upper floors of the building, where you maybe don't want to have weldable rebar on some of the steel members. You don't want to engage the steel frame in that way. So you can just use the overall compression of the elements as the frame tries to deflect to resist the overturning forces and shear forces that are on that design. You can see a couple different sections here. So hybrid designs are certainly going to be kind of a specialty type of element that you can utilize within steel. You could also use it within concrete frames and buildings anytime that you add in the masonry elements after the steel or concrete elements have been put in place. Shaft walls. Shaft walls are certainly going to be elements that we like to see being used as shear walls, mainly because they really doesn't generally change the design of the shaft, making it a shear wall element. The boxed wall group, that I like to call it, has a lot of stability, a lot of capacity. Making sure that we don't have any movement joints in these elements is going to be important to make sure that we can take full advantage of all of the capacity of the boxed wall groups that are in there. If we do add in movement joints, what we do is we essentially break the walls apart into different pieces, where you have walls in one direction and then perpendicular walls for the other direction, but they're not talking, they're not working together, they're just operating individually, and we just see a lot less stability and capacity in those designs, right? If I take a boxed wall group and I pull it apart into individual plate elements, I have about half the capacity that I would have if I allow it to be a boxed wall group. So just kind of looking at some of the capacities that we have here for a boxed wall groups, certain design loads that we have on the design. What we find is we see the along the walls that are in parallel with the shear force, those are going to be the shear resisting elements, and then the flanges are really going to be the tension and compression elements. So we have a pretty high ability to resist forces with that in mind. If I have individual walls, though, I have really only the walls in the direction of the load that resist all of the moment and shear. So I can have a lot less, say, moment capacity, of a lot less of an ability to place reinforcement away from the centroid. So we do have oftentimes a lot less capacity in those situations for the design. So this is just one example. In this case, it was about half the capacity by having individual walls instead of a boxed wall group. So again, keeping all of those walls together do give us a lot more capacity. We can see that whether this is going to be 2 stories all the way up to 10 or 12 story buildings, we see boxed wall groups being very effective elements for the overall design of these buildings. Now, certainly looking at different design forces and stresses all the way up, those elements is certainly going to be things that we need to take into account as well. Masonry shear wall details, different details that are utilized for the building certainly have a large impact on the overall shear wall capacity. One of the first things that I'd like to talk about is the movement joints, control joints that you have within a shear wall design, long walls versus short walls. If you have long walls, so control joints that are far apart, we actually have far more capacity in resisting shear forces, overturning moment forces, than if I have a bunch of short walls. So obviously there's a balance. We have to take into account the too far. If you try to make them too long, you could run into some cracking due to thermal loading if you don't have the right amount of horizontal reinforcement. So there's a balance that we need to take into account. But just as a really simple example, just showing the one additional movement joint here in this elevation, we have about a third of the capacity. We lose about a third of the capacity with the upper diagram is what we have with the lower diagram. So again, some of the different models that we set up, you can see again with the 8-inch walls, F'(M) of 2250, 20 feet tall, 24 feet long for the long walls, and 3 of them, which would be equal to the what we have on the right, the short walls, where we would have 18 feet long and 4 walls. We have different design capacities due to the length of the walls, due to the overturning moment, and you can see that's where that 33% increase comes from when we can just have the longer walls with more overturning moment capacity. Now, maybe for the design, it's shear that controls, and then obviously in that situation, they're going to have very similar shear capacities just due to the exact same length of wall. So it's when you have a moment capacity that you're considering. Taller walls certainly have more of a moment demand. Shorter, more stout walls are going to be more of a shear load dependent design. Other things about movement joints that are important in terms of shear walls, making sure that we have control joints away from openings. And certainly where we put those control joints is going to be an engineering judgment. Just my personal engineering judgment is I'd like to keep control joints at least 2 feet away. That's not within a code. It's not anything other than my recommendation for placing of control joints relative to openings. So just a really quick example of this. If we look at an elevation in an unreinforced wall, the code does allow us to put those joints right at the opening. And that's, again, when we just have a purely unreinforced design, that's when we would look for maybe having a control joint in that location. But that's not typical for most of our structural walls. Most of our structural walls have reinforcement in their designs. And so once we have reinforcement, the CMHA Tech Guide 9-25 has some really good discussion and illustrations of this movement joint locations. So moving them away from the openings is going to be a lot better for the overall performance of the design. We have the reinforcement vertically and horizontally to prevent any cracks from occurring from the corners. We can then do a lot of things with the lintel design that's going to make it much better. We're going to have some arching action that we can account for. But then the wall, we have a perforated shear wall. We have a long wall that has an opening in the middle of it. Certainly we have a lot of forces and stresses that we have to account for. But again, I think we have the right tools to do this today. We have several different software programs that allow us to model perforated shear walls and have a good behavior of those different wall panels accounted for. So each of the different regions would have its own moment and shear that we can utilize and look at for the overall wall design. Very simply, it looks like this. We just simply have an opening in the middle of our wall, and so that's going to have a lot more capacity. So again, looking at this one more time, if we have 2 short walls, again, just looking at a really simple example, having 2 short walls, we're going to have a lot less overturning moment capacity than if we have 1 long wall. So this wall has about a third of the capacity that this one does. And so that does make a pretty big difference. We have a lot of buildings today that have a lot of openings. We have clients that are asking architects, that are asking engineers to have a lot of perforated walls. And perforated walls doesn't mean that we have to lose a lot of shear wall capacity. We can allow the openings to be within areas where control joints are moved away from the openings, and we can still have a lot of capacity in these designs. So again, just a really quick example for this design. We can look at 2 of the similar type models, one with a perforated wall where we have a 96 kip capacity at the top, versus two short walls where we have far less shear capacity, again, just due to the overturning moment that we can account for the two different designs. Now, certainly I could take the short walls and I could add a lot of reinforcement and I could beef up the capacity of short walls. And so I could do things to make that design work. But again, if we're comparing apples to apples, perforated walls do have a lot more capacity than movement joint at the opening. And we can take this example and go a little bit further with it. If we have large dock doors, maybe a fire station, maybe dock doors on a building, or maybe this is just a series of windows, large windows on a building, we can move movement joints away from these elevations. We have good presentations on just movement joints where I talk about this at some length, but moving those control joints away can increase the overall shear capacity, shear wall capacity of this elevation fairly significantly. So we want to make sure that we take into consideration where movement joints go in all openings, but certainly if we have a series of openings that are stacked up one after another, we want to make sure that those movement joints are away. We utilize this whole elevation for the building. Now, that may be for that area. We can go to standard control joint location for the rest of the building. We just have one area that we have minimal control joints. Certainly, again, having the right finite element analysis so that we can look at the overall forces and stresses. We can look at the moment capacities, moment demands on each area of the lintel. We can see that the lintel elements in these perforated shear walls are going to be meshed wall elements that are going to tie into and be fixed to the meshed wall elements for the jambs and wall areas on each side of the opening. But again, we're going to have a lot more capacity in these designs. We're going to have a lot better understanding for what the overall lintel design would look like. So where movement joints go make a big difference in the overall shear wall design capacities, but it also makes a big difference in terms of lintel designs, lintel capacities, and the ability for that lintel, that element above the opening, to still participate in the shear force resisting system for your design. So a little bit more about the details, again, just to summarize some of the different reinforcement details that we talked about a little bit earlier. All of this reinforcement information is going to be from the code and giving us different provisions for where reinforcement's going to go. If we have an ordinary reinforced or an intermediate reinforced or a specially reinforced shear wall element, we do have different areas where those different elements can be utilized. And I think this CMHA Tech Guide 14-18B, it's a little bit dated, but it still has some really good information and all of the where the different types of walls can be, the ordinary, the detailed, the ordinary reinforced, or the intermediate, where the different seismic design categories that they can be utilized, where you need to use specially reinforced and how that can be utilized. But it also has some really good information for allowable stress design, strength design, pre-stress design, some good indications there. Again, a little bit dated, but I think still very good information for designs. The guide also has some very nice details for what some of these elements look like. For here is going to be reinforcement options for non-load bearing elements in seismic design category C and higher. But then it's got some very nice detailed diagrams for where all of the reinforcement that we talked about in that summary, the joint reinforcement or the number 4 bar horizontally at 10 feet on center, the vertical reinforcement at 10 feet on center maximum, but at the ends of the walls at each side of an opening, making sure that we have reinforcement that goes past the edge of the opening, at least 24 inches or 40 times the diameter of the bar. Reinforcement at the top of the walls are all going to be important for the ordinary reinforced masonry shear wall. Now, again, if we go to the intermediate, really the only difference between the last slide and this one is that the vertical reinforcement is going to be 48 inches on center maximum. So it's a really simple change that you'd have between ordinary and intermediate. And then if we go to the specially reinforced, we know that we have more vertical and horizontal reinforcement relative to the overall 1/3 of the height or 1/3 of the length parameters. Other than that, it's going to have some pretty similar provisions. So again, nice little detailed guides for ordinary, intermediate, and specially reinforced walls. Just a few examples for the designs. We're going to use a couple different software programs and kind of walk through some of the different options that you have, some of the different softwares that we'll look at. We're going to use Masonry for some of the component design, shear wall examples, but other programs are out there as well. The direct design program from CMHA. You also have Quick Masonry and TEDS that allow us to look at shear wall designs. For the finite element analysis, you can see the examples earlier from both RAM Elements and RISA. In this example, we're also going to look at a wall design for the Tekla Structural Designer for masonry shear walls. But before we use some software, what we'll do is go through a really quick example by hand. And what we're going to do is we're going to use the Masonry Designer's Guide. We're going to look at this page 19-103 from the Masonry Designer's Guide from 2016. Just looking at a really simple 21-foot 4 wall, 16 feet high, 2 feet to the top of the parapet. We have axial forces that we have of 44.3. We have shear forces of 25.55. And we have a moment of around 408.8 foot kips. So for that, we can do the axial compression check that we have in the wall. We can look at the different equations for capacity for axial forces. Our F prime M for the wall, we're going to use 2,500 PSI. We can see the overall strength equations for the design, and then we can look at the flexural capacity based on that axial force that you have in the design. Again, for the moment load of 408.8, phi factor of 0.9, MN required is going to be 454. From that, we can see, based on the overall length of the wall, the reinforcement cover that we have, the overall D, our area of steel, 1.2. So 6 number 4 bars, area of steel required be 0.4. So we're going to be okay for the area of steel that we have versus what would be required for the design. So real quick axial check and flexure check. We also can look at the shear loads, the shear capacity that you have for the design based on the equation 6, based on the moment to shear times the length of shear wall provision. We know that we have 218.7 kips of shear capacity, so we know that that's okay. We certainly could also add in additional horizontal reinforcement and additional capacity for the shear walls if we needed, but again, we didn't need that, so that's certainly very good. So again, so the detailing of the wall, we know that we have an 8-inch wall, number 4 at 48 inches on center, 3 number 4 bars horizontally, or joint reinforcement at 16 inches on center would work just fine for that design. Now, what we can also do is we could look at a wall like this in our different software programs that are available. We could look at this here within the RAM Elements program. You can see what the overall load would be on the wall. You can see, again, we can look at some of the axial capacity curves, axial moment curves. You can see what those different provisions are. It's going to give us a final design capacity status and then give us all the different capacity equations as well for that design. At the end of the day, for that simple shear wall, we also are going to get a detailed elevation for the reinforcement that's utilized in this design. So a very simple check for the shear wall as well. A couple other different examples. Masonry is a very nice program for looking at shear wall design. We can look at a very simple wall, 16 feet tall, 24 feet long, F prime M of 2,500, reinforcement number 5 at 8 feet on center. We could look at this with an in-plane force of 2,500 pounds per foot. We can see that that wall without having any axial force on it is not going to be sufficient for the overall design. If I change that wall, if I add some axial force, just a simple 2,000 pounds per foot load with the same in-plane force is going to give us an in-plane axial check of 0.613. I'm sorry, in-plane check, the interaction equation 0.613, axial check of 0.08, so we know we're well within the vertical limitations. If I add even more load, you can see that again, same interaction equation for the in-plane check, and I have my axial check, my interaction equation goes up a little bit. Obviously, I'm adding more load. So adding more load, we can certainly add in more moment capacity, have a better overall design if we can make that shear wall a load-bearing shear wall versus just a non-load-bearing wall. For finite element analysis, again, for a simple plain wall, we can certainly develop those capacities. If we wanted to look at the interface between the different wall elements and what would be a wall group, even a three-sided wall group that I have here, so I can have the overall design, number 5 at 24, for this wall with that's going 4 different stories in the design. We can model this into Tekla Structural Designer. We can look at the overall stiffness of this element, the overall forces and in-plane shear forces that I have developed on these floors and assigned to these rigid diaphragms at each level. And for that, I can look at the overall capacities of each of the different wall panels. For each floor would have a different capacity. Certainly, I could change the reinforcement at each floor. I can look at optimizing the overall capacity for this wall design. So with a finite element analysis, I certainly have a lot more ability to look at a lot of different elements pretty quickly, but I also look at them as interconnected elements that have inherently more capacity in their designs. So really quick conclusions, types of shear walls that we have. Again, we can look at the different walls that we have. We have unreinforced and reinforced. Masonry shear walls, obviously reinforced is going to be better. Load-bearing walls maybe make unreinforced possible, but again, a little bit of reinforcement goes a long way. Hybrid walls, anytime that you have a frame and you have an infill of masonry, we certainly can develop some shear wall capacity from those masonry elements. Perforated walls, just the walls with openings, again, utilizing those elements, developing a lot more capacity than individual walls on each side of the opening. So perforated walls are definitely the way to go, having the right software tools to do that design. Wall groups, anytime that we can have a boxed wall group or even a C-shaped wall group, we have a lot more capacity as we look at the interface of those different elements design. We have several different finite element analysis tools. RAM Elements, Risa 3D, Tekla Structural Designer, all give us different perspectives on those wall groups. But again, if we just have the simple reinforced masonry shear wall, Ella Masonry, Quick Masonry are going to be nice tools. We have direct design. We also have the Tekla TEDS program that gives us some really good capacity equations. So with that, if you do have any questions, feel free to reach out to me at sam@forceconsulting.com. Thanks for being with me today.